Good morning, all. So, today we shall study some problems on partial differentiation. Let us see the first problem. If y is equal to e raised to minus I into bracket omega t minus kx, you are asked to show that dou 2y by dou x2 is equal to k square upon omega square dou 2y by dou t. So here you are given y as function of x and t, and you are asked to show that dou 2y by dou x2 is equal to k square by omega square dou 2y by dou t2. So since y is equal to, we have the given expression for y as e raised to minus I into bracket omega t minus kx, we can differentiate y partially with respect to x. So we get dou y by dou x as dou by dou x of e raised to minus I into bracket omega t minus kx. So that the differentiation of y with respect to x partially will give us e raised to minus I omega t minus kx as it is into differentiation of this term, power term, with respect to x partially gives us ik. It is into ik, and this term is nothing but y. So this can be expressed as ik into y. So dou y by dou x works out to be equal to ik into y. Now differentiating this dou y by dou x once again partially with respect to x, we will get dou 2y by dou x2. Therefore dou 2y by dou x2 is nothing but dou by dou x of dou y by dou x, and dou y by dou x is ik e raised to minus I omega t minus kx. So differentiation of this will give us I square k square e raised to minus I omega t minus kx, or this is equal to minus k square y. This is nothing but minus k square y. So this is the expression for dou 2y by dou x2. Now we can obtain the expression for dou y by dou t. We have dou y by dou t is equal to dou by dou t of y, and y is e raised to minus I omega t minus kx. So this gives minus I omega e raised to minus I into bracket omega t minus kx, or this is nothing but minus I omega y. This term e raised to minus omega t minus kx is nothing but y, so this can be expressed as minus I omega y. And differentiating dou y by dou t once again with respect to t, we get dou 2y by dou t2 and this is nothing but dou by dou t of dou y by dou t, and dou y by dou t is minus I omega e raised to minus I omega t minus kx. So differentiating this bracket with respect to t partially, we get minus I omega into minus I omega is I square omega square e raised to minus I into bracket omega t minus kx, or this is equal to minus omega square y. This term e raised to minus I omega t minus kx is nothing but y. So this I square can be replaced by minus 1. So it becomes minus omega square y. So let us consider this is equation number 1 and this is equation number 2. Now taking the ratio of equation 1 and 2, we get taking the ratio of equation 1 and 2, we get dou 2y by dou x2 divided by dou 2y by dou t2 is equal to dou 2y by dou x2 is minus k square y divided by dou 2y by dou t2 is minus omega square y. So this y cancels, minus minus will cancel. So this is nothing but equal to k square upon omega square. So we can write the expression transferring the term in the denominator here to the right hand side. We get therefore dou 2y by dou x2 is equal to k square upon omega square into dou 2y by dou t2, and that is what we are asked to prove. So if y is equal to e raised to minus I omega t minus kx, we are asked to show that dou 2y by dou x2 is equal to k square upon omega square dou 2y by dou t2, and that is what we have proved. So that is this first problem. Now let us see the second problem. Problem number 2 is if f given as the function of x and y and is expressed as x cube y minus e raised to xy, you are asked to show that fyx is equal to fxy. And also you are asked to find the expressions for fxx, fyy, fyyy and fyxx. If f is given to be this function of x and y, you are asked to first show that fyx is equal to fxy, and also you are asked to find the expressions for fxx, fyy, fyyy and fyxx. So let us first try to obtain the expression, first try to show that fxy is equal to fyx. So for that purpose we have to differentiate f partially with respect to x and y. So since f is equal to x cube y minus e raised to xy, this will imply differentiating f partially with respect to x will get fx, and fx will be equal to dou by dou x of x cube y minus e raised to xy. So differentiating partially with respect to x, we get fx is equal to 3x square y minus y e raised to xy. The differentiation of e raised to xy is e raised to xy into the differentiation of xy with respect to x is y only. So this is the expression for fx. Now we can differentiate f partially with respect to y. So fy, this is fx, fy will be equal to dou by dou y of x cube y minus e raised to xy. So differentiating this f partially with respect to y, we get x cube minus x e raised to xy. So fy works out to be equal to x cube minus x e raised to xy. Now we want to first show that fyx is equal to fxy. So differentiate fx partially with respect to y and then differentiate fy partially with respect to x. We get fxy and fyx. So fxy will be equal to is nothing but dou by dou x of dou f by dou y. Fxy is nothing but dou by dou x of dou f by dou y. So this is nothing but dou by dou x of dou f by dou y is x cube minus x e raised to xy. So fxy can be expressed as 3x square minus e raised to xy, 3x square minus e raised to xy minus yx e raised to xy. So here we have the product of two terms. So we have to apply the product rule for differentiation. So first differentiating x, keeping e raised to xy constant, we get this differentiation. And then keeping x constant and taking differentiation of e raised to xy with respect to x is y e raised to xy. So that is the expression for fxy. Similarly, we can obtain the expression for fyx, and fyx is nothing but dou by dou x of this is fxy is x is dou by dou y of dou f by dou x, or this is dou by dou y of dou f by dou x is 3x square y minus y e raised to xy. So differentiating this dou f by dou x partially with respect to y, we get dou by dou y of 3x square y is 3x square, and dou by dou y of y e raised to xy, we have to apply the product rule here. So this is minus e raised to xy minus y x e raised to xy. So this is the expression for fyx. This is the expression for fxy. So from these two expressions, we observe that fxy is equal to fyx. So we have proved that fxy is equal to fyx, and this is nothing but equal to 3x square minus e raised to xy minus xy e raised to xy. So that is the expression for fxy and fyx, and both the expressions seems to be one and the same. So the first identity we have proved. Now we want to obtain the expressions for fxx, fyy, fyyy and fyxx. So we have the expressions for fx and fy. So let us obtain the expressions for fxx and fyy. fxx is nothing but dou by dou x of fx. fxx is nothing but dou by dou x of fx. So this is dou by dou x of fx is 3x square y minus y e raised to xy. So differentiating this bracket partially with respect to x, we get 6xy minus y square e raised to xy. So this is the expression for fxx, 6xy minus y square e raised to xy. This is fxx. Then we want to obtain fyy. fyy is nothing but dou by dou y of fy, or this is dou by dou y of fy is x cube minus x e raised to xy, and differentiating this fy partially with respect to y, differentiation of the first term will be 0. Since this term does not contain y, its differentiation will be 0, and with respect to y, if we differentiate x e raised to xy, it gives minus x square e raised to xy. So this is the expression for fyy. So fyy is minus x square e raised to xy. Now we want to obtain the expression for fyyy. So to get fyyy, we have to differentiate fyy with respect to y partially, or this is nothing but dou by dou y of fyy is minus x square e raised to xy. So fyy will be differentiating this term once again partially with respect to y, we get minus x cube e raised to xy. This gives minus x cube e raised to xy. And finally, we want to obtain the expression for fyxx. So fyxx is nothing but dou by dou x of fyx, and this is nothing but dou by dou x of fyx. Fyx is nothing but 3x square minus e raised to xy minus xy e raised to xy. So differentiating this fyx partially with respect to x, we get 6x minus y e raised to xy, uh, partially with respect to x, we have to apply the product rule here. So minus y e raised to xy minus y square x e raised to xy. So that is the expression for fyxx. So if we are given this function f of the two variables x and y, we can obtain fxy, fyx, and we observe that both these expressions are one and the same. Again, we can find out the expressions for fxx, fyy, fyyy, and fyxx. So that is how we can obtain the expressions for these partial differentiations. So let us see the next problem. The problem number 3 is the equation of state for 1 mole of perfect gas. The relationship between the pressure, volume and temperature is given by Pv is equal to RT. We know the expression for 1 mole of a perfect gas as Pv equal to RT. Now, if we have this equation for the perfect gas, 1 mole of perfect gas, we are asked to show that T dou P by dou T at V, dou P by dou T at V into dou V by dou T at P is equal to R. We are asked to show that T dou P by dou T at V into dou V by dou T at P is equal to R. So let us start from the given equation. We are given the perfect gas equation as Pv is equal to RT. So since we are interested to obtain the expression for dou P by dou T, let us express this expression for P as RT upon V. So differentiating this expression for pressure P partially with respect to T, we get dou P by dou T at constant volume V is equal to R upon V. We will get dou P by dou T at V is equal to R upon V. Now we want to obtain the expression for dou V by dou T, so that we can write the expression for volume as V is equal to RT upon P. Since PV equal to RT, we can write V is equal to RT upon P. And differentiating this expression for volume partially with respect to temperature at constant pressure P, we get dou V by dou T at P is equal to R upon P. We will get dou V by dou T at P is equal to R upon P. And now, taking the product of dou P by dou T at V and dou V by dou T at P, we get therefore dou P by dou T at V into dou V by dou T at P is equal to, the expression for dou P by dou T at V is R upon V, and the expression for dou V by dou T at P is R upon P. So this is equal to R square upon PV. But we are given that PV is equal to RT. So using this value of PV here, we can express this as R square upon RT. So this 1R will cancel. So we get the expression for dou P by dou T at P into dou V by dou T at P is equal to R upon T, and transferring this T to the left hand side, we get T into dou P by dou T at P into dou V by dou T at P is equal to R, and that is what we are asked to prove. That is what we are asked to prove. Okay, so next problems we'll study in the next video. Okay.